Hello, everyone. I'm sorry I'm not there in person to deliver this talk, but I appreciate the opportunity to do it remotely like this. I want to talk to you today about streaming graphs and streaming graph processing and highlight some of the work we do in this space. Graphs are quite ubiquitous right now. They're all over the place. And there are estimates that the market by about 2026 will be over 4 billion US dollars. Some others expect that the growth will be about 100% annually over the next little while. If you look at the distribution of the DBMS marketplace, graphs are still relatively small component. They're about 1.8% of the marketplace, but really, and the relational dominates. But if you look at the growth rate of these systems, you will notice that the graphs are the graph databases are growing really fast. And this is expected that the growth will continue, and some expect that by 2030 the marketplace will be over 11 billion US dollars. In whichever statistics you look, the cumulative annual growth rate seems to be over 20%. So it's a really healthy marketplace. And as you can imagine, the marketplace is full of companies. This is as of 2019. I'm sure it's richer now. If you want to get a little bit more into where the landscape is and what are important, I refer you to this Communications of ACM article that came out of a Doug Schul workshop in 2019, December, that some of us participated in. One other thing that I wanted to point out is a pair of papers that report on user studies. I was involved in this user study back in 2018, and we asked users what their pain points were with respect to graphs, and then we extended it by doing more user interviews and became a VLDB journal paper. The major findings are not surprising. The graphs are indeed everywhere, and they are large. And machine learning workloads on graphs are quite prevalent in this space. Scalability remains a major challenge, followed by visualization and query languages. It's not easy to write queries for graphs because of lack of a schema. Relational systems still play a role. They're not going anywhere, and they play a role in this space. And there's a disconnect between what we study as academics and in terms of the types of graphs that we look at, such as web graphs and so on, that we like, and what the user community is focusing on. And that's an issue that we need to address. So today, what I want to talk to you about is an important graph type called streaming graphs. And these are graphs which combine the streaming aspects, which is that we have unbounded data. Streaming data is characterized by unboundedness. Data keeps coming, and you don't actually have the capacity to store and then process it. So you really need to do it as it comes. So this requires non-blocking operators and algorithms. And usually these data come at high speed so it has real-time constraints. And the graph aspects, which is that the streaming, what comes as streaming are typically edges, and the vertices may emerge as part of edge arrivals, but it's typically edges, and the graph emerges over time. You don't ever have the graph. An example use case is what Alibaba reported. They have very large graphs, about 500 million active users and 2 billion catalog items and that they manage. And the relationships among these are important, so the graphs are important. And they process 320,000 transactions per second, and that's a lot. and they need to process petabytes of data in real time, and that's a real-time constraint. So what I want to do today is to talk about what we mean by streaming data processing. So that's the baseline, and then talk about how these show themselves in graph processing. So we focus on stream graph processing. And then I'll talk a little bit about what we do in this space as part of the Esgraffito project, and then conclude. So let's do the streaming graph processing. Streaming data is part of big data. Without defining what big data is, we typically talk about 4 V's of big data: volume, variety, velocity, and veracity. And streaming data deals with the velocity aspect of it. Data is not static. We call static data at rest, and streaming data in motion. So this is data in motion. They arrive at the system and they're unbounded, as I said, and there are many examples of these types of data. Data stream systems, which is the generic term I'll use and I'll define in a bit, they take as inputs some data that is generated by one or more sources that are generated in real time, and they arrive at the processing site in some fixed order, typically timestamp order. There are, of course, in real life, they can come out of order, but let's ignore that complication for now. They come to the processing site, we do some processing on it, and then we generate outputs, and the outputs are generated in real time, and the answers are up to date because we're continuously generating them. And there are many applications for these that you can imagine. There's a stark difference between our traditional DBMSs and DSSs. Traditional DBMSs, we store the data, so the data is persistent. And when we want to retrieve something from the data, we pose a query, and the query is transient. We pose the query, it gets executed on the persistent data, and we produce a one-time result. If in a week I want to pose the same query again, then I pose it again. It's another query that goes through the stuff. Yes, I know stored procedures, but by and large, this is the workflow in traditional DBMSs. In DSSs, by contrast, queries are persistent, and the data is transient. As I said, data comes continuously, and it's unbounded. So the queries are persistent, and as data comes, we need to identify which queries will be affected by this incoming data, and execute those queries. Typically, incrementally execute those queries and generate results. So the results are continuously generated. So if you want to think about it one way, in traditional DBMSs, we index the data and use that to execute queries because we want to determine which part of the data we should access. In DSSs, we index the queries, so when the data comes, we can quickly determine which queries we need to incrementally reevaluate. So they're really quite opposite of each other. In addition, there are other differences. DSSs are typically push-based. Data is pushed, as I talked about unboundedness, and the stream conditions may not be stable. Velocity might change, workloads might change, and you could have data drift that I'll talk about at the end of my talk. There are 2 classes of these systems that I separate as old versus new. The older systems, the objective was to provide typical database functionality that we see in relational databases, provide that functionality over streaming data. That was our focus. This work started in early 2000s and continued until about late 2000s. And there are examples of these systems that were built: Stream, Gigascope, Telegraph CQ, Aurora, Borealis. And by and large, all of these systems were single machine systems, except Borealis. And our focus was really on figuring out how to build this functionality. Towards the end of 2000s, these systems went into hiatus and kind of died down. And in mid 2010s, they were regenerated, and that regeneration more or less coincides with the emergence of MapReduce and Spark, where the focus was not on providing full database functionality, but just providing simple processing platform. And then if you wanted to build database functionality on top of it, that was on you to do it. And this new class of systems that I call data stream processing systems, the SPS, really is in that class. Apache Storm, Huron, Spark Streaming, Flink, etc. They don't provide full database functionality. They just provide the platform for processing streaming data. And you could do what you want on top of them. And these are almost all scale-out systems. So there is this difference between the old DSMS, which is data stream management systems, and the new DSPS, data stream processing systems. If I don't want to make a distinction in my talk between the two, then I would call them data stream systems, DSS. So the typical reference architecture for this, nobody builds systems in this fashion, but the typical reference architecture for this is shown in this figure. What we really have is data comes, streaming data comes, and they are put into an input buffer that I'll come back to in a minute, but they're stored in working storage. And the queries, persistent queries, are recorded in this query repository. They're registered there. So this repository manages persistent queries. And then these queries are executed over the data in the working storage in the query processor. That's the typical reference architecture. And then the results are put into output buffer and streamed out. Now, the working storage, from the data in the working storage, we typically take a summary of it, because as the data comes and moves, we lose the old data. So we do typical sketch-based summaries and store those summaries if we want to refer to what happened in the past. And that's the summary storage. And in many of these streaming systems, you want to be able to access static data, data at rest, as well as data in motion, and that is stored in the static storage. We keep this input monitor is important, because if the incoming data rate, for example, is higher than our processing capability, then we need to do load shedding, intelligent scheduling, etc., and that's all done by input monitor on the input in the input buffers. So this is the typical way to reference architecture for persistent query processing. And of course, when you go to analytics, the only thing that changes is that the workload is not persistent queries, but they're analytics applications, and the engine is not a query engine, it's an analytics engine. But we can assume the rest remains the same. Now, the data model for streaming is fairly simple. It's an append-only sequence of time-stamped items that arrive in some order. So we talk about the data model as a tuple of timestamp and payload. Payload is whatever we get. It could be a relational tuple. It could be graph edges, as we talked about. Revision tuples are those where the source says, what I sent you, it was wrong, I'm updating it. And the timestamp is attached typically by the source to say, this is when I observed this data. So this is a very simple data model. So let me now talk about how the streaming manifests itself over graphs. I'm showing you here a timeline, and these are timestamps. And at time t0, nothing happens. We don't have anything happening. At time t1, edge AB comes. Above this line, I'm showing you the arrival of edges. Below this line, I'm showing you the emergence of the graph. And the time on the timeline is the timestamp, and the edge that comes, AB in this case, is the payload. And then time moves forward. Sometimes nothing happens. Sometimes new edges come, and the graph emerges more, and it goes on like this, and it emerges, and eventually you notice here that at some time along this line, you might get multiple edges. That's possible. You can get multiple tuples with the same timestamp but different payloads that generated. And eventually at time t12, you get an edge deletion happening. And that's possible. Some of these graphs are monotonically increasing. Sometimes you have explicit deletions, which makes life more difficult. And if you have edge deletions from T9 to T12, as you can see, the graph has changed. And these systems combine two difficult problems, streaming and graphs. Streaming brings the unboundedness and high rate, and we know that graph processing is computationally heavy and difficult. So this is a challenging scenario to operate in. I should, at the outset, make clear that streaming graphs and dynamic graphs are different things. In dynamic graphs, you really have the graph wholly at hand. Usually, in the case of in the sense of vertex set, we have at least the vertices, and edges arrive and they're updated. So that's a dynamic graph, and the updates could be either to the topology structure, we have edge arrivals or edge deletions, or it could be to the properties. If we are talking about property graphs, attribute values can change. Streaming graphs, you do not have the whole graph ever in your hand. It emerges, and you have to basically deal with this emerging graph. So it is important to emphasize that the streaming graphs and dynamic graphs are different. In literature, a lot of the streaming papers that have streaming in their titles are indeed addressing dynamic graphs, not streaming graphs in the sense that I'm defining here. Streaming graphs have applications. Fraud detection in e-commerce is one. We're basically, in this case, observing transactions made by users and establishing these connections between the users who's making the charges and the merchant, and looking for certain patterns to determine credit card fraud. Similarly, there are applications that do intrusion detection in networks, typical denial of service attack, where we look at the TCP packets, in particular the header information, and see if we have this denial of service attack towards a single victim in that. So there are real applications. Let me talk about the streaming graph computation models. There are two types. One is continuous. This is where you process each edge as it comes. And so you get the edge AB as the payload with an indication of what the operation is, insert in this case. So that's your payload at time t1, and we process it. And then time moves on, and then you process these as they come. Some insert, some deletes. And you can do simple processing on these. You can do filtering, for example. Those are possible. These are transactional operations. But this requires linear space if you want to do anything more, and that's unrealistic. So this is an old 2002 result, which basically says if you want to do anything serious with this type of streaming data, then you need unbounded memory, which we don't have. Therefore, many graph problems are not solvable in this model. Theoretical computer scientists talk about a semi-streaming model, that can operate in sublinear space, and they assume that the entire vertex set is available and the edges are streaming. As I talked previously, this is the dynamic graph model, not streaming. The other alternative is windowed model. We define a window. So in this case, our window is from T5 to T10, open on the right, closed on the left. And if you look at the graph snapshot in that window, this is what you have. And you basically execute do whatever processing you do on this particular snapshot graph. And then the window moves, and you incrementally do the computation when the window moves and a new snapshot emerges. When a new snapshot emerges, sometimes you lose some edges from here because they fall out of the window, and new edges will come that will enter the window. So that's window. And you can do a lot more with windowed processing. So graph streaming workloads are typically of two types: graph querying, or what are called online querying workloads in literature. This is basically the case where there's a query and the query accesses either a portion of the graph or it might access the whole graph, but typically a portion of the graph that can be assisted by an index. But even if it accesses the entire graph, it's one pass execution, and you're done. And there are two types of operators here: navigation queries and subgraph matching, and I'll talk about these a little bit more. That's graph querying. Graph analytics is unclear, the definition of graph analytics. Typically in the graph space, this has referred to applications like PageRank, clustering, graph mining, etc., which are iterative workloads. You keep processing the graph, you touch the entire graph, and you keep iterating over the graph multiple times until you either reach a fixed point or a termination condition. That's one definition. Another definition is, of course, the analogous thing to OLAP over graphs, the thing that we do in relational databases, and this is how you support analogs of operations such as rollup, drill down, slice and dice, etc. And there is some work in this space as well, but we never really know what we mean by graph analytics. So that we probably mean both of these applications. And these are all done under a stream of updates. That's the important issue. The updates are coming and done on unbounded data. A little bit more word about graph query language requirements. As I said in the previous slide, graph query models should support two types of queries. One is navigation queries, the top one that I'm showing here. I'm showing it both as a figure. P knows X who works for Y, who knows F, and F knows other F, and that. Or it is data log equivalent in red on the top. Or and it should also support subgraph pattern queries of the type that I show in the model. So there are this is true for any graph query, not only streaming, but any graph query model should support both of these. And it should support the ability to query both the topology, structure of the graph, and the properties. Most of our work focuses on topology, unfortunately, in the graph domain. We should support paths as first-class citizens. Typically, in many of the works, paths are a sequence of edges, which is fine, but that doesn't allow you to use paths as first-class objects with predicates on the paths themselves, for example. A typical query language, graph query language, should also support closedness. Typically, is similar to what we have in relational languages. That gives you closedness, which makes the closedness is the property that you take one type of input and you produce the same type of input that can be an input to the next operator or the next query. So this is how you compose more elaborate queries. These query models and languages should lend themselves to be translated into an algebra. If we're going to really have sophisticated graph DBMSs, we need to study and see how we do the algebraic execution engines of relational systems. And for streaming, particular requirement is that these should lend themselves for incremental computation, because you're not going to be doing computation from batch. And just as a passing note, the recently announced GQL as an extension of SQL does not satisfy all of these, I don't think. Right? At least the question is that you should ask yourself is if GQL satisfies these. All right. With that, let me talk about what we do in this space and go. This is part of the sGraphito project. And our objective was to both study this query the processing here and to study analytics over these streaming graphs. And we wanted to do it within the context of a common framework. So if I put it into this framework, I have the querying capability at lower and the analytics capability above it. So I want to be able to do both in one system, similar to EdgeTap. We're far from this. We don't know how to architect these systems. But at least in our sGraphito, what we did is that we defined one type of data model, and the same type of data model goes through both of these cases. So what is that the underlying data model? We're working with property graphs. I'm sure these are well known. These are graphs that have attributes attached to both vertices and edges. We work with the streaming edges. So the payloads for us, the payloads are streaming edge, and we call that a streaming graph tuple, SGT. And as you can see, and here I show you a sequence of edges that arrive, or the SGT that we see. And we work in time-based windows, so that's a window. And we, more specifically, we work with time-based sliding windows. So for us, there are two parameters. One is window size, and the other one is slide interval. So the window size might be, for example, for fraud detection, might be 1 week, and the slide interval might be 1 day. So we slide the window every day and do the incremental recomputation, looking at the data for 1 week. And we treat each window as a snapshot, and we do processing on that snapshot. And as the window moves, as I said earlier, the snapshot changes, and we do incremental computation on the snapshot. So let me talk about the streaming graph querying part. This is part of two particular theses. Anil did the query processing, query models, etc., and Karen then looked at cardinality estimation. So we're talking about this part of the architecture now. So what do we need to support here? What we need to support here is incremental computation, as I said. We need to support unblocked operators, because we never see the end of the data. We need to support windowing, because that's the domain, that's the framework we operate in. And if we want to support time travel queries are basically those where you say, how did the data change over time? Then you need to support temporality. Somehow keep track of the evolution of the graph. We don't do this. This part, the fourth point, we do not do yet, but that is important in streaming context if you really want to do that. Our objectives in doing all of this were to follow a principled approach similar to what we do in relational DBMSs, and follow that principled approach to generating a system that can evaluate persistent streaming graph queries. Okay, so we defined a formal model that we call streaming graph queries. We showed its semantics and proved its equivalence to a subset of data log. We developed logical algebraic primitives to translate these and showed the equivalence, so the completeness in that sense. We developed a query processor where we have some incremental and non-blocking operator implementations. More implementations are possible, but we basically gave exemplars, one implementation for each operator, just to demonstrate that it's possible, and specific algorithms for doing regular path queries, navigation queries. And we did the optimizer, which is really query planning and optimization in this case. So we really were looking at this entire pipeline of that we commonly see in relational systems, and we focused on all of these steps except the parser, and our optimizer is built on top of Calcite, and our execution engine is timely data flow because that gives us certain properties. And then we later looked at the statistics that we feed into the cost model. So I'll quickly go over these. So our streaming graph query model, at the top, I'm showing you an adaptation of an LDBC query where we're basically looking at people who are following and liking the posts of other users. And if you notice, we have a pattern on the left, and we want to repeat that pattern until we reach a point. So this example contains both a subgraph query and a path query. We treat paths as first-class objects, and so on. And these are all the desirable properties that I talked about earlier, and we fulfill all of those properties. We're careful there, and we have a clean semantics, which is non-recursive data log and a clean star. So that query could be written as this non-recursive data log. The first line gives you the subgraph part of the query. The second gives you the path, the repetition there. Then we actually developed logical algebra operators that can be used for these. And these we came up with this filter union because we're working in the window scan pattern for subgraph pattern, and the paths as first-class objects for the path expression. Some of these are heavy-duty operators, but we do have them, and we prove that you can take any SGQ expression and map them into the algebra. So we have this completeness property. So just to give you an example for this algebra, I'm showing you on the left, top left here, a G-core representation of the query that I've been talking about. We use G-core as the basis here and added some streaming properties, but that's the query. We can write that as an algebraic expression of what we've done, and then we can transform that into a query plan of the type that I'm showing here to produce the answer. Okay, so these are still algebraic, logical algebra query tree. Okay, this is part of that. And then what we worked on is the physical execution. Now, at the storage layer, we store everything as relations because we're using the timely data flow as execution engine, and it's easier to deal with those. So our operator here is our typical, the join, union on the right, etc. On the left is the logical plan that I showed you, and on the right is the equivalent physical plan that you get. And each of these, union, join, etc., has implementations that capture the particular operators on the left. And there is a direct mapping here. I'm not going to go through these in detail, but the color coding shows you the mapping that we typically get in this case. Okay, so talking about optimization, what can be optimized? Of course, we can optimize alternative. We can have alternative operator implementations. As I said, we didn't go through that too much. We gave exemplary implementations, but more implementations are possible. You can have alternative query plans, and we did investigate those. And you have the typical problems. How do they define equivalence? What order do you execute, and so on. And then the query optimization is your typical query optimization problem. You have a search space, you have search algorithm, and you have to have a cost function. And we built this on top of CallSight. Really, we defined a bunch of transformation rules to get this moving. Some examples here I'm showing just to demonstrate, but I'm not going to go through those. For each of these logical operators, we've defined transformation rules. So we have these equivalences, and we prove the correctness of these equivalences, of course. And then we map them into CallSight, where we encode both the transformation rules and the implementation rules, which is really how you map the logical operators to the physical implementations. And the next thing that we really do is to explore the plan space. So the question that comes up is that what other alternative plans are possible, and do these make a difference? So I'm showing you a simple query here, which is a clean star of a concatenation of edge labels. And on the left, I'm showing you 7 different plans to execute this. All of these will get you the result. And on the right, I'm showing you that the measured processing time per window for each of these plans. As you can see, the execution time changes quite a bit. So yeah, there is value in looking at different alternative execution plans and determining which one is better. So there's clear difference here. Okay, so given that we have multiple plans and these plans seem to make a difference in the execution cost, of course, the natural question that comes up is how do we select between these plans and so on. And this is the old problem of cost optimization, and we use cost-based optimization. We implemented that, so we need to have a cost model. So one of the things in this cost model that we need to capture is the streaming graph characteristics, and these characteristics are independent of the operator implementations. And there are 2 of these, which is one is the rate of the streaming graph. The other one is the average validity, the length of validity of the intervals. Based on these, we need to compute or estimate the resource usage. And the typical metric that's used for this is unit time cost model. This is old, it's not our invention. This actually requires us to define the average cost of operators per unit application time. And we also have to devise specific physical operator implementations. And then the plan cost is really the summation of all of these. And then we map these to CallSight, of course, and as extended metadata catalog to store these estimates. And the cost functions for each individual operator. Now, we did this using a simple model for estimation. And when we look at the estimated versus measured for the same plants that I showed you, we see that they match the estimated plant behavior across different plants is the same as the measured, but the y-axis, which is really actual values, differ quite a bit. And that's partly because of the way that we do estimation that needs to be improved. So the next problem we tackled was that of the cost model and statistics, particularly statistics that we feed into the cost model that we've defined, and that requires the cardinality estimation that leads into the estimation of intermediate results. So selectivities. So how do we do that? Let me just a quick primer. When you do cardinality estimation and graphs, you need to decide where you do it, and let's consider the storage layer. At the storage layer, we store things as edge tables. So if we have these two edges with two different labels, label A, label B. Now we have these two edge tables, one table per label, and then when there's a query that looks for a pattern like the one that I show at the bottom, then it requires a join between these edge tables. So that's typically the execution model, and that's the execution model we have in as part of timely data flow implementation as well. So of course we can have multiple edge patterns, and we've identified these. And the joint predicate changes, as you can imagine, whether it's a source or a source target. Source refers to the fact that the V1 is the source of both of these edges. So when we're doing a join of V1, V2 edge with V1, V3 edge, we're joining on V1.source. And similarly the others. The predicate changes, but they can be approached similarly. So in cardinality estimation in streaming graphs, there is no technique. There are techniques developed for regular graphs, but not for streaming graphs. So we took as our baseline what we had originally implemented, which is SystemR, and adapted the SystemR approach. Just to remind everyone what SystemR approach is, if we have this particular query at the top and this execution tree, and this I sub AB is the intermediate results generated from the join of A and B. The SystemR approach says, let's compute the cardinality of this binary join at this level, which is given in this formula, and then we propagate that up the tree and to get the results. Notice here that the distinct targets of I sub AB are estimates that we generated in the previous step. So SystemR makes all these assumptions about inclusion, uniformity, and independence that are well known. But the problem with the SystemR is that these assumptions do not hold, and as you go up this execution tree, error propagation starts hurting you. So we did this study. The star query is a query where you have one vertex in the middle and you have edges coming out of this one. So star 4 says there are 4 edges coming out of it. Star 8, there are 8 edges coming out of it. Since our query plans are binary query plans, as you can imagine, star 8 query plans are deeper than star 4, and that causes this error propagation where the Q error, which is a common metric that is used to compute the error in these plans, is fairly high. And that's an issue. So our question was, can we do better? And we developed a sketch-based technique for doing it. So first is the data structure, which is GraphSketch, that we developed. So the GraphSketch is is simply a summarization of the original graph. So at the top, I have the original graph, and for simplicity, I have all of these edge labels, the same label, so I don't have to deal with multiple tables and so on. And then we basically decide a user-defined parameter, which is the number of buckets. Let's assume that we choose 3 buckets. So then what happens is that each of these vertices are hashed to a bucket, and then we generate edges between buckets depending on the edges that exist in the original graph. So if 42 hashes into bucket 0 and 10 hashes into bucket 1, then there's an edge from bucket 0 to bucket 1 in the bottom. And the edge weights in the summary graph are really how many edges there are in between these buckets. And as you can see, sometimes you have edges inside within the bucket as well. And that gives your matrix which shows from this bucket to that bucket how many edges we have, and that's easy to detect. We also the graph sketch also maintains two arrays, distinct source and distinct target vertices. And again, since we have 3 buckets, the first entry is bucket 0, the second entry bucket 1, the third entry is bucket 2, and each of these basically says from bucket 1, bucket 0, how many outgoing edges there are. In this case, there are 3. If you count the edge weights of the edges coming out of bucket 1 in the graph, you will see that. So that's the structure that we generate. That's graph sketch. Fundamentally, the graph sketch is the matrix plus these 2 arrays. Then how do we do cardinality estimation with graph sketch? We basically come and generate the graph sketch, construct them for the leaf nodes. So these are where I have 3 leaf nodes, A, B, and C. So I have these graph sketch matrices. I'm not showing the arrays, but you can easily develop the arrays. Then when I have a query like this, I do a pattern match based matching on the stream, and then compute the statistics and propagate them. So really what happens is that I take this MA and MB, these should be reversed, and do the estimation on what is going to be done based on the pattern to generate the matrix for this intermediate part MAB. Which is for the IAB, the intermediate results. And then I keep doing it until I get to the source, and the total number of counts in the root matrix is the expected or estimated number, the result set for this particular query. So that's how we do the estimate. In this case, that's 4. So in the streaming context, of course, the window moves and we get potentially a new matrix at each window. So let's consider this a graph in window 1, and you can easily generate your matrix as such, assuming again three buckets, doing some hashing, and we have these 2 arrays. And in window 2, we delete this particular edge between 220. Now, of course, the graph sketch needs to be updated, and the baseline is that I can compute the whole graph sketch from the snapshot in window 2, but we don't want to do that. We want to do this incrementally, and we can do that. Let's assume for a moment that the vertices 20 and 200 both hash into bucket 3. That actually means I need these to be updated. And incrementally, I can simply update those and get these results. And that will satisfy what I want, what we want. So in the streaming context, we do this graph sketch updates incrementally. The rest of the estimation is done per window. We compute the estimation on the particular persistent query that we're looking at. Now, when we do the same analysis for GraphSketch that we did for System R, we noticed that the Q error is much, much lower, even as we increased the query complexity. We do have reasonable Q error. It increases, of course, because there is still the propagation delay, but nothing like what we get in System R. But the critical thing, this is only one aspect. The critical thing is, does improving Q error have any impact on choosing better plans? And this has been recognized in literature as a significant issue. People develop techniques for better estimation with lower error, but they cannot demonstrate that this has any impact on query plan selection and latency. So we did another analysis, and I'm showing you only one of our analyses. We basically said, okay, so if we give it 109, if we look at what GraphSketch does when we have one bucket, and GraphSketch with one bucket is equivalent to System R, and what GraphSketch does with 900 buckets, do we see any changes? And as you can see, for each query type, we see quite a number of plan changes. So this leads us to the conclusion that GraphSketch and GraphSketch-based cardinality estimation is indeed quite effective. So that's our work on the querying side. I'll quickly talk about the graph analytics. This requires a talk of its own, so I'm only going to give a highlight, not much more than that. So again, now we're basically focusing on this aspect of this our objective, and really our objectives in this part, our ultimate research goal is to create an analytics engine to perform machine learning aided analytics stacks over streaming graphs. And the research looks at three issues. One is exploratory analysis of real-world streaming graphs. We do that to identify hidden patterns and correlation in streaming graphs. What is that? And the goal is to learn fundamental graph characteristics that affect performance of algorithms. So this is kind of a data-driven approach. We study these graphs, capture some some characteristics, and use those characteristics to develop algorithms. The second one is we want to do representation learning over graphs, and the question here is one of modeling. Given a stream of unbounded graph events, which are graph edge insertions, deletions, etc., how do we embed the most recent content, which are feature vectors, and local structure to each vertex in the graph? So how do we actually model that, and how do we explain the emergence of patterns in graph streams? So if you take motifs, and we're talking about streaming, these motifs will emerge over time, just like graph is emerging over time. And how do those emerge? What is the model that explains those? And finally, we do analytics, some analytics over streaming graphs, and we tackle two things: motif counting and drift detection. And in this study, we focus on bipartite graphs, which are really graphs where the vertices fall into two classes. What I show here are the green is one type of vertex, and yellow is another type of vertex. For example, if you take Amazon's graph, it is of this type. Some of these vertices are users. Some of those other vertices are items, and the edges between those are users buying items, users reviewing items, users liking items, etc., etc. So we focus on bipartite graphs because a wide variety of real-world connected data records naturally occur in bipartite mode. These are quite common. And real-world graphs, all real-world graphs have an underlying bipartite structure, so these are important, and they capture really well the pairwise relationships. And for motifs that we're looking at, both in terms of task 2 and task 3, we focus on butterflies. Butterflies are 2x2 byte clicks, and the red here is a butterfly or byte click, and because they are really main driver of graph behaviors such as sensitivity and degree of sortivity and so on. And so these are building blocks. And the challenge here is that because we're in a streaming context, we have some real-time constraints. So being able to do this processing efficiently, so we do it on each window, but when the window moves before the next window movement comes, that's the time span we have for doing all of this analysis. So that's difficult. And we really want to be effective, that we do not generate too many false, inaccurate results. So in our exploratory analysis, our findings, we had a number of findings. We identified what we call butterfly densification power law, which basically says the number of butterflies at time t follows a power law distribution of the number of edges at t. And then we discovered temporal motifs. Butterflies as network motifs can emerge across the timeline, and we discovered their bursty emergence, that the butterflies come and they emerge as a burst, and then emerge as another burst sometime later on. So we from analysis of real world graphs, we had a number of these results. In terms of modeling, again, we basically wanted to do the modeling on the emergence patterns of this. How can we model so we can predict the emergence of these butterflies in streaming graphs, and that those identify the generative origins of these patterns. And these are helpful for ML graph benchmarks and so on. And we developed this model called escrow, which captures real well the emergence or the growth model for butterflies. Again, butterflies over bipartite graphs. Finally, on the graph analytics, we focused, as I said, on two tasks. One is approximate butterfly counting. The accurate or counting or exact counting is really quite difficult, and they won't work. So we use approximate, but we want approximation to be quite accurate. And again, achieving that accuracy along with efficiency is a challenge. And the other challenge is that really these bipartite streaming graphs are triangle free. So any technique that is based on triangles in the graph won't work. The final piece of work that we looked at is concept graph detection. Since you get data over time in the streaming data, the characteristics of the data are likely to change over time. And this change could be in many of these different types that I demonstrate below. And this is a really hard problem to detect. And we have algorithms to be able to detect these over time in streaming graphs. Again, bipartite graphs and motifs. And so we're talking about changes in that motif part. All right, so let me conclude with a few remarks. Streaming graphs are real, and they occur in real-life applications. They're important for real-time decision making. And we really haven't paid in the community too much attention to streaming graph challenges. We spend more time on dynamic graphs, but less on streaming graphs. But as I argued, they're not the same. So you need to be careful, and particularly unboundedness in streams causes real challenges that I outlined. And this unboundedness in space under edge addition and deletion is a significant issue that is a theoretical bound. And the field is quite open, and there are very interesting problems, but it's really challenging. So let me end there with a thank you to my collaborators, Ida and Anil were my PhD students, and Karen was my master's student, continuing on to PhD, and Angela Bonifati is my collaborator at the University of Lyon. And I thank you for listening.